Right, so I'm going to show you how Bob and Alice can make a decision without actually knowing what each of their options are as part of that decision. So the method I'm going to show you is an oblivious transfer, and it relates to scrambled circuits. So it's highly relevant to a world where we can ask somebody if they're over the age of 18 without actually them revealing our age to us. So in an age of privacy and privacy preserving, then the usage of scrambled circuits and oblivious transfer is highly relevant. Okay, so I've got an example here, and I'll just explain the basic principle. But what we've got is that we've got Bob and Alice who agree something or not. So a zero is a false, and a one is a true. So if we say we're going to use a logic function of and, so they've both got to agree to something, and Alice makes a true yes. She wants to go, and let's say it's to a concert. So let's say that Bob says no and Alice says yes. Because we're using the and, then we get a zero, so they won't go. But if Bob says yes and Alice says yes, then hopefully, then they both say yes, and we can reveal it. So what we really want to do is to make sure that Bob and Alice can't know what the decisions are, but for us to receive a verifiable output. Okay, so this is the basic model that we're actually going to use for it. Okay, so we have Bob and Alice here. So we can create any logic that we can, but we'll keep it quite simple just now. So what we'll have is an AND function. So with an AND, so Alice and Bob. So with an AND function, 0 and a 0 gives a 0, 0 and 1 gives you 0, that gives a 0, and then that gives us 1. Okay, so we're going to end up with four different options there, four different results for the logic. So we'll define that as Z. So what Bob is going to do is that Bob is going to encrypt each of these outputs with a key, with his key. So let's call this A here and B. And what we'll do is we'll encrypt with we'll encrypt for this output, this output, this output, and then this one. So this will be, we will use a key for A equal to 0, and here we'll use a key for A equal to 0, and a key for A equal to 1, and a key for E is equal to 1. Okay, so we're going to use two keys there. So then what we'll do is that we'll also have another key for B equal to 0, another key for B equal to 1, a key here for B equal to 0, and a key here for B equal to 1. Okay, so and then the two keys are then used to encrypt these values. So we'll have an output here, and we'll call that cipher 1, cipher 2, cipher 3, and cipher 4. So Bob will send those ciphers over to Alice. So Alice now has four ciphers, cipher 1, 2, 3, and 4. And then what he does is he passes over the key that relates to his decision. So let's say that Bob doesn't want to go to the concert. He sends over key equal to 0 here. Okay, so that goes over, and then Alice has that key. And now what we do is we use what's called oblivious transfer to be able to get Alice's key over to her for her decision. So she's going to make a decision, say, of true. She wants to go to the concert. So what happens is that she makes the decision, she sends it over, and Bob can't tell what her decision is, but will generate the right key for us. So if you're interested, I've got little examples of oblivious transfer of the cryptography that's used here. So we can pass her true or false back using something like discrete logarithms, then we can generate the right key for her. So she also gets the key for her decision, which is this key here that's been used. Okay, so we now have two keys. A is equal to 0 and B is equal to 1. Now, so this was the key for 0, 0. So Alice doesn't know that. This is the key for 0, 1. This is the key for 1, 0. And this is the key for 1, 1, 1. So then Alice will take the two keys, decrypt, nope, it doesn't work. Decrypt, yes. So this one will actually work when we decrypt it, and she'll get a value of 0. So it means that the decision is that we will the answer is false to the decision. She tries the next one, it won't work because it's the wrong keys, and she tries the next one, and that doesn't work either. Okay, so in this way we can actually we can create a logic. A logic can be anything that we want. So we create our logic here. We then encrypt all of the values, send the keys over, and then Alice will only be able to select the one that corresponds to both their decisions. At the end of it, Bob doesn't know Alice's decision, and Alice doesn't know Bob's decision, but you can see here that they have come to some agreement. If we were using an OR function, then obviously those would become 1, 1, and 1. Then when we cipher, it's the same process again, but in this case the output for corresponding to this option will be a 1. Okay, so we can create really complex operations here, and we can pass the keys that are required, and in this way we can actually hide our decisions. Okay, so if you're interested, here's the code that I've generated in Python to show a basic operation. So hopefully we'll be able to get, so for an XOR, either Bob and Alice can agree, but not both of them together. And then we'll see, in this case, if we use a 1 and a 1, we get 0, a 0 and a 1 should give us 1, and so on. Okay, so that's scrambled circuits.